For millennia, mathematicians have been able to calculate the volume of shapes like cylinders and spheres, but only thanks to painstakingly derived formulas. But what if you have a shape that doesn't have a formula? What if it's huge or underground where you can't fill it? There's a method so powerful, it forms the basis for calculating fuel tank capacities in aircraft, determining the volume of water storage tanks in cities, and even modeling blood flow through arteries in the human body. Today, I'm going to use it to figure out how much water this vase can hold, without pouring a single drop. But first, we need to talk about a powerful tool: integration. In a nutshell, integrals find the area under a curve by adding up an infinite number of rectangles with infinitesimally small width. Surprisingly, this idea is hidden in plain sight within the notation. Let's start with the dx, something often forgotten when writing integrals. Dx, or delta x, represents a small change in x's value. Think of it this way. If you're walking along the x-axis and are taking tiny steps, dx represents the length of each step. In integration, these steps become infinitesimally small, so small that they approach zero width. Each rectangle has this same tiny width, dx. Now, what about the height of each rectangle? This is where the function f of x comes into play. If we're finding the area under a curve, each rectangle needs to stretch from the x-axis up to the curve itself. At any point x along our curve, the function f of x tells us exactly how high the curve is at that location. So f of x becomes the height of our rectangle at position x. Different values of x give different heights, which is why our rectangles vary in height as we move along the curve. This leaves us with the last piece of the puzzle. What does the integration symbol mean? We can figure this out from how we describe integration. Since an integral sums up an infinite number of rectangles, the symbol just means infinite summation. So the notation literally tells us what it's doing. It's taking an infinite sum of rectangles, where each rectangle has area equal to height f of x times width dx. I should point out, this is not a rigorous proof, but rather an intuitive conceptual breakdown. But what does this have to do with finding volume? Well, what if those pieces aren't rectangles? Let's go back to the vase. After taking some measurements, I've determined that the vase's height is 19 centimeters, its top width is 8.4 centimeters, and its bottom width is 10 centimeters. Then, I took a picture of the vase, carefully making sure that my phone's angle was aligned with the vase in order to accurately capture its dimensions. Additionally, I put a stick inside the center of the vase, also making sure it wasn't angled. After opening the image in Desmos, resizing it so that 1 unit in Desmos equals 1 centimeter, and making sure the stick is on the x-axis, we are ready to get started. The reason for doing this is since we don't know the vase's shape, we are going to outline its top half with functions. Okay, so after a lot of trial and error, I've determined some functions to fit the vase's top half. Since the vase has two distinct curves, one that's curved downwards and one that is straight going upwards, I've decided to come up with two equations, one to describe each part. For the first half, I got y equals 0.45 times sine of pi over 13x minus 18 over 125x plus 5.2, where 0 is less than x, which is less than 13. Then, for the second half, I got y equals 52 over 345x plus 1.36, where 13 is less than x, which is less than 18.75. Now that we have these equations, what do we do with them? Let's give them some names. I'll call the first one R1 of x, short for radius 1, and the second one R2 of x, for radius 2. Together, these equations describe how the vase's radius varies as x changes value. Remember earlier when I asked, what if those pieces aren't rectangles? For area, we added up thin strips, but for volume, we need to add up something else. Picture the vase lying on its side. If we cut off an extremely thin slice, that slice wouldn't be a rectangle. It would be a circle, like a coin. That's our disc. And if we add up all those discs from one end of the vase to the other, we can find the vase's volume. But how do we turn that into math? By treating each disc as a cylinder, we can use the volume formula pi r squared h. In our case, h is just the thickness of the slice, an infinitesimal dx. So, substituting that in for the height gives us pi r squared dx. Since each disk has radius given by our function, we get pi times r of x squared dx for each slice's volume. Then, by integrating, or taking that infinite summation of disks, we get the total volume. The integral of pi times r of x squared dx. And just like that, we've discovered the disk method. Since we have two functions for the radius, r1 of x and r2 of x, we'll need to use two integrals, one for each function. Then, the bounds of the first integral will be the bounds for r1 of x, so 0 to 13, and the second integral's bounds will be r2 of x's bounds, from 13 to 18.75. Many integrals of this form become tricky, sometimes even impossible to reasonably solve by hand, so we can use a calculator like the TI-84 to solve these. Doing so and then adding them together gives us the total volume of the vase, which is approximately 1,114 cubic centimeters. We would be done, except, what good is a vase without flowers? So I went to the store and bought some. Here's the thing, by adding these flowers to the vase, it will affect how much water the vase can hold. Is there a way to measure that? For simplicity, we'll assume that the stems in the bouquet form a cylindrical shape. The actual shape of the stems is not very consistent, especially near the top of the vase, but this keeps the geometry simple. One approach is to find the volume of the stems using pi r squared h, and then subtract that from the vase's volume. That's perfectly valid, but since we've been using integrals, what if we tried that approach instead? Following the same technique as the disk method, we can use the integral of pi times r of x squared dx, where this time r of x represents the radius of the bouquet. Giving it bounds from 0 to 18.75 and then subtracting it from the other two integrals accomplishes the same goal. But I want to show you something more elegant. First, let's split this new integral into two parts, one that goes from 0 to 13 and another that goes from 13 to 18.75. Because these two integrals now match the bounds of the two integrals we used to find the vase's volume, we can use integral properties to combine each pair of integrals with the same bounds. This gives us a new form. The integral of pi times big R of x squared minus small r of x squared dx, where big R of x is the outer radius and small r of x is the inner radius. This is the washer method. Why? Thinking back to the disk method, we found the entire volume. But now, some volume is taken up by the bouquet. So if we look at a single slice, By subtracting that inner volume from the disk, we are left with a disk that has a hole in the middle, which looks exactly like a washer. Now, for the moment of truth. By measuring the diameter of the bouquet and dividing by 2, we get that the radius is 0.875 centimeters, meaning that r of x equals 0.875. Plugging this into our equation for the washer method and using our calculator gives us the final volume of approximately 1,069 cubic centimeters. Since 1 cubic centimeter is equal to 1 milliliter, we get that the vase's volume with and without the flowers is 1,069 milliliters and 1,114 milliliters, respectively. Let's see if our estimates are correct. After using some measuring tools, I've determined that the vase's volume without flowers is 1,144 milliliters, and with flowers is 1,113 milliliters. Based on our expected answers of 1,114 and 1,069 milliliters, and our observed measurements of 1,144 and 1,113 milliliters, we can calculate the percent error using the formula the absolute value of observed minus expected divided by expected times 100. This tells us how far off our estimate is from the right answer. Doing so gives us 2.69% and 4.12% for each calculation, which is remarkably accurate given our approach. And there you have it. We successfully measured the volume of this vase without pouring a single drop of water. What makes this approach truly powerful is its flexibility. In our example, the bouquet's radius was constant, but it doesn't have to be. In fact, the inner radius can be any function we want, so long as it's less than the outer radius. This is what makes the disk and washer methods so amazing. By using calculus's ability to account for instantaneous changes in functions, we can find volume of any shape, so long as we can describe it mathematically. Thanks for watching.